important method that you can do with canonical correlations is use them as a tool of dimension reduction. So usually when we're working with multiple x's and multiple y's, it can be difficult to plot their associations. If we want to see the association between academia with our psychological variables, what we'd end up having is we'd plot all 3 of our x's with all 4 of our y's. And in that case, we'd have 4 x values, 3 y values, for a total of 4 times 3, or 12 scatter plots, which is usually way more than we want to actually look at. So instead, what we can do is just plot each pair of our canonical correlations, and that'll capture the strongest relationship possible between our x and y values. And instead of having to create 12 scatter plots, we'll just have to create the smaller of p and q. And in our example, we'd only have to plot 3. And this method allows you to look at the strongest associations possible between uncorrelated pairs, and it'll also allow you to see if there are any usual observations. Are there any outliers in the data that may not show up, even when you're looking at pairwise comparisons? And as a quick example, let's look at our chapter 10, when we're looking at the bones on the right side of the body compared to the bones on the left side. And because we had 4 bones for y, 4 bones for x, that means we have a total of 4 canonical correlations we can calculate and 4 sets of canonical variates. If we look at v1 with u1, we have a correlation of almost perfectly 1. And when we look at it, that's exactly what we see. We have pretty much a straight line between v1 and u1, our combination of x with our combination of y. The next set of u and v are going to be the next highest correlation that you can possibly get, while these two, if you kind of plot them versus one another, will be perpendicular or uncorrelated with one another. And we can see that they have a correlation of about 0.92. And if we're looking at the third strongest one, it still has a correlation of 0.87. And there's not really many unusual points for 1 and 2, but there appear to be some outliers as far as the third canonical variates go, especially these 2 people over here and this 1 person up here. So maybe we can see what's unusual about these 3 skeletons. And if we're looking at the fourth canonical correlation, the last one still has a really high correlation for being the smallest one at 0.74. And again, there are some unusual cases that we can find looking at these scatter plots. Since there are 4 x's and 4 y's, usually we have to create 16 scatter plots. This way we only have to create 4. What does that look like in R for our data? We can use our basic plot function. If you do cc1 $canonical variable y, or can vary, you run this and you put this little 1 out here, it's telling it to just look at the first column. So these are the values of the first canonical variate for y, or u1. And there should be 600 of them, and that's exactly how many we have. And we want to plot those against their x values. So convar x, canonical variate x, the first one will be u1. And then just use this paste function to say the canonical correlation r1 is equal to whatever the first value is. When we run that, we can see that the canonical correlation is about 0.45, not very strong. And the scatter plot agrees with it. There doesn't appear to be a strong association, even when you're looking at the best combination of x's with the best combination of y's. So it appears then that your academic performance doesn't really tell us anything about your psychological self-worth. And as we go down, U2 with V2, U3 with V3, we kind of expect these to get worse. This has a correlation of 0.15, and if just looking at the scatter plot, would think that was a lot closer to 0 than it is what we have here. Looking at the third one, correlation of essentially 0, scatter plot agrees, the correlation is essentially 0. And you can use this for loop to kind of run through them quickly. So S is 3 because that's the smaller of P and Q. So it's doing the same plots that we have up here, just running through the ith column of Y with the ith column of X. I have it change its colors, and then using these paste functions, we can figure out what our correlation number is, what the correlation value is, along with what v number we have and u number that we have. Running this line, it's just going to spit out the same 3 plots, just does it a lot quicker, using one set of code instead of 3 separate sets. We mentioned that one of the nice properties of canonical correlations is that their variates outside of their matching pairs are all uncorrelated. So if you take any y with itself, or if you take any y with its different covariate, so u1 with u2 or u1 with u3, or in our case, we have u1 with v2, those should all be uncorrelated with one another. If we run our scatter plot, that's what it appears to look like. No strong association between u1 with v2, and if we calculate the correlation between the two, we get computationally 0. So a nice tool you can use with these canonical correlations is reducing the dimension of your data to see how closely related your variables are. Anytime we're creating new variables, often a goal is to try to figure out what these combinations are. So what is u1 representing, or what is v1 representing from our original data? And essentially, again, we're taking a weighted combination of the y's to create a new variable, a weighted combination of the x's to create a new variable, and the goal is to create a highly correlated pair. So what elements of y are highly correlated with what elements of x? Which, unfortunately for us, we mentioned that while the correlations are invariant to the scale, doesn't matter if we're looking at feet or inches, these a's and b's, the eigenvectors, do depend on the scale of the original variables. And so if you change them one variable from feet to inches, it'll make the value on its eigenvector smaller since the scale increased. So to remove the effect of scaling, we just want to go ahead and standardize them. And we're going to standardize it kind of the same way we did in Chapter 8 when we standardized our discriminant functions. We'll take our original scales and just multiply essentially all of them by their standard deviations. So this dy is going to be a diagonal matrix with the standard deviations on its diagonal for y, and this dx is going to be a diagonal matrix with a standard deviation of x on the diagonals. That way, these a's and b's no longer depend on the scale, and that makes them easier to interpret. But you can only interpret them once they've been standardized. You wouldn't want to interpret the raw coefficients. And the idea is that these standardized coefficients show how much each variable is contributing to this new u or this new v that we're creating. And what you need to do is if you delete one of the variables or add another one, you kind of have to redo this entire process as the coefficients and your correlations will change. So you can't just add in a new variable and expect everything else to stay the same, because that's what ends up happening when you're dealing with multivariate data. Adding a new variable, especially if it's highly correlated with an existing one in y or x, will cause everything else to shift accordingly. So if we standardize our variables by hand, what we can do is create our diagonal matrix for y. So what we'll do is we'll take our original variance matrix for y. This diag command will make a vector of just the diagonal part of syy. These are our variances for the 3 variables. We want to turn them into standard deviations. Anytime you turn a variance to a standard deviation, you just need to take the square root. We want to create a new matrix from that, and the diag function, if you give it a vector, will turn it into a diagonal matrix. The diag function is pretty smart. If you feed it a matrix, it turns it into a vector of the diagonal. If you give it a vector, it turns it in to a diagonal matrix with that vector on the diagonal of it. And then we'll do the same thing for x. So that's the standard deviations of reading, writing, math, and science. And then we'll standardize them by taking our original coefficients. Maybe a little tempting to want to interpret these as basically saying u1 is just a combination of your control versus your motivation. How much control you think you have in your life versus how motivated you are to achieve something. But because these variables have different scales, if you notice that control has a lot larger variance than motivation does, we want to rescale them. And we'll just throw the names on it so that way I can keep track of what these coefficients belong to. And now if you notice, control makes up the majority of U1. And you can kind of think of our first canonical variate for y as being something like 2 parts control versus 1 part motivation. We're kind of adding those two together. 2 controls plus 1 motivation. And then concept is pretty small relative to the other two, so you can kind of ignore it if we're interpreting it. So the first canonical variate for y appears to be values control is important plus about half of your motivation, which makes sense. You'd kind of expect how much control you believe you have on your life will determine how motivated you are to achieve your goals. The second one appears to be motivation, and then we're going to combine control and concept together, subtract out motivation. I don't know that much about psychology. Maybe that makes sense to a psychologist, but to me, I can't really think of anything. And then the third covariate for y is mostly concept, so it appears that the last one is mostly just the concept variable. That's typically what you're going to see if you're dealing with uncorrelated y's or uncorrelated x's, is that the first variates, or that the variates themselves are essentially just going to be the individual variables themselves. If all of the y's were perfectly uncorrelated with one another, your first canonical variate would be one of the variables, your second one would be another variable, and your last one would be the remaining one. We can try to do the same thing for the x values, see what our 3 new x covariates are. And the first one looks to be a combination of your reading and writing ability. Makes sense, you may want to combine those together. The second one appears to be writing and science. We saw those two were pretty strongly correlated. And then the last one appears to just be an overall combination of all 4. Just adds the 4 of them together. Well, it adds writing with science and reading with math. So it combines reading your math scores together, your writing and science scores together, and subtracts them. And whatever that works out to be is something, if you know how to interpret it, that could be your new V3, whatever that is interpreting with. And then we can kind of try to figure out what those may have in common. And it appears that your concept of control is the most correlated with your ability to read and write. Your concept of motivation is most correlated with your writing and science abilities. You can also get those without having to standardize them by hand, using the CCA function again. If you say x scale equals t, y scale equals t, it'll standardize the values for you. And you can see we end up with the same results that we did by doing it by hand. So this time, if you standardize them, they will give you back exactly the same values this time around. And we're not going to go through the slides for them, but you can also do hypothesis tests. As long as we assume that both x and y are multivariate normal, we can do some methods of inference to figure out how many of these canonical correlations are statistically significant, actually have a relationship with one another versus just random noise that may exist. If you call up CC1 chi-squared, it's going to be the test statistic for a chi-squared approximation. So for the null hypothesis that all 3 of our canonical correlations are 0, we end up with a test statistic of 146.7. Chi-squareds depend on their degrees of freedom, so this could actually be a small test statistic if the degrees of freedom are large. This is our null and alternative hypothesis that it's testing. Rho is going to be the population canonical correlations. The null assumes that they're all equal to 0. The alternative isn't going to say that none of them are equal to 0. It's just going to say at least one of them is not equal to 0. And since the first one is the largest one, if only one of them is not equal to 0, we know it's the first one. You can calculate a test statistic, and what that function r is doing is it's taking this lambda 1, and you can look at the previous slides to figure out how to calculate it, turning it into a chi-squared variable by taking the log, multiplying it by something that makes it less unbiased for a chi-squared distribution, and then the degrees of freedom we're going to use for a chi-squared is just p times q, the number of y variables times the number of x variables. For us, that should be 3 times 4, or 12. And if we look, that's exactly what our degrees of freedom are. If you do cc$1.df, it gives you that chi-squared's degree of freedom. And our first one is 12. Our second test to see if the second and third one are both equal to 0. So we're dropping out the first one because we believe it's statistically not equal to 0. So we'll just check to see if the second and third one are equal to 0. Well, we end up with a chi-square test statistic of about 14.5. And what its degrees of freedom are is we'll take p minus 1, q minus 1, and multiply those together. So we'll take 3 minus 1 times 4 minus 1 gives us 2 times 3, or 6. And then the last one is going to test to see if just the third canonical correlation is equal to 0. Is it statistically different from 0? And if we look back, our sample canonical correlation is 0.023. That's really close to 0. We end up with a small test statistic. And we can use this p chi-squared since we have the chi-squared value and its degrees of freedom. We want to say lower tail equals false, so that way it finds the upper tail of a chi-squared instead of the lower tail. Running it, our p-value for all three of them being equal to 0 is 0. Our p-value for the last two being equal to 0 is about 0.025, so somewhat statistically significant. And then the p-value of the last one, this 0.023 being equal to 0, is pretty large. It's close to 1. And you want to remember, though, when you're doing your hypothesis test, is just because something is statistically significant doesn't mean that it's actually useful. Looking back at our canonical correlation between x and y, while it may not be statistically equal to 0, there may be a correlation between the two. If I want to use these x's to predict these y's, there's not much I can really use with it because the strength of the relationship is pretty low. So using academics to predict your psychological values wouldn't be that accurate. When you're dealing with smaller samples, in this example, we have a sample of 600. 600 is pretty large. But if you're dealing with a smaller sample, an F approximation is better than a chi-squared approximation. Looking at how to do an F approximation on the slides, it's not that pretty. So we'll just let R do the heavy lifting for us again. You can do an F approximation in R from that same package as a function f.test.cca. All you need to give it is your canonical correlation model, and it'll give you your test statistics. For some reason, it doesn't give you anything for the last one. I don't know why. Because if you do it out by hand, you can get a F value, a denominator degrees of freedom, and a P value. But this function decides to not give it to you. The correlation is pretty small anyway, so probably not statistically significant. But if we're looking, we actually end up with the exact same results that we did for a chi-squared approximation. Because as your sample size grows larger and larger and larger, these denominator degrees of freedom get bigger and bigger for an F. It gets similar and similar to a chi-squared. If you notice, the numerator degrees of freedom are the same. And our p-values that we found earlier of 0.0249 are the same ones that the F approximation gives us. But repeating over again, just because something is statistically significant doesn't mean it's practically significant. You always want to look to see if that statistically significant relationship is actually useful for you achieving your goals, whether it's trying to figure out how your academic and psychological variables are related to one another, or maybe if you want to see if you can predict somebody's psychological scores based off their academic ones. In our case, not recommended. Whereas if we're looking at our bone example from chapter 10, these all appear, even the fourth one, to be very, very strongly correlated with one another. So there are strong associations with the left side bones to the right side bones. So in this case, they're both practically and statistically significant.